My name is Eduardo Madrid. I am going to introduce you to information theory in the form of delta coding today. And I don't have much in the way of source code to show you because in my trial runs, I have seen that a lot of our colleagues benefit more from learning the principles than seeing them in action. If I would show you libraries of these, then we will have to go in quite a lot of detail. But the good news is that there are good libraries that are open source that exercise delta coding, such as Google protocol buffers in particular. And there are plentiful resources to pick the techniques from the source code available of different projects. But again, what they don't do is to explain the principles behind the whole thing of information theory and delta coding. And without the benefit of looking at the code, we're going to be able to discuss actual mistakes that, for example, Google has made in the specification of delta coding that they use. And I hope that, that you guys like it. For those of you that don't know me, I have been working as a tech lead or a team lead for several organizations in different areas of software engineering, like high-frequency trading and startups like Snap, the maker of Snapchat. And what they have in common is that we have been doing a lot of infrastructure for performance and efficiency. And part of the work that I've done is to provide guidance for team members to get much better at C++ and so that they are able to do top-level quality software infrastructure. I have presented at the conferences and users groups, such as, for example, London C++, about some of my inventions and the topics that I'm interested in. And this is a small sample of what they are about. And I am putting here delta coding with a question mark because we will talk about several issues that prevent us from making a generalized delta coding library. In particular, that we don't have reflection or introspection in the language yet. So that is something that I'm not sure that I'm going to tackle right away. What are we aiming to do today? Provide you with guidance so that you can, in practice, apply delta coding for the benefit of your applications, okay? For that, we need to introduce information theory. And doing that is going to give us the opportunity to have an intermediate depth discussion about the relation of delta coding to several things that I am listing in this slide, okay? One thing that I always make mention to my audiences is that my slides are not to be read in the presentation, but they work as a reference material afterward when you want to revisit the topics that we cover about, okay? For some people, I know that it is distracting because they are presented with what I am saying to you right now, and also with the alternative in the slides, and we get out of sync, and please, I'm gonna do it one more time. If the improvements keep happening as they have been happening in regards to that fact, then I'm gonna continue doing it. If not, then I might change my style to present. But bear with me for a moment. Okay, delta coding. What is exciting to me to share with you about delta coding is that these techniques are useful all by themselves, but they also serve as the entry point to a world of improvements in our abilities to do software engineering, in my opinion. I believe that they are empowering, okay? So let's motivate delta coding. What we're aiming to do is to do algorithms to compress data of our applications in a way that is very easy to implement, effective, and has really great performance, okay? So let's see why we might be able to do that. What are the things that we might be taking advantage of for the purposes of achieving easy-to-do compression that is highly performing? Okay. The thing is that when things change, the magnitude of the changes tend to be much smaller than the things themselves, right? So perhaps it is more efficient to start with a snapshot to capture the state of something, and from that point onward, only apply the changes that happen to that thing, as opposed to redrawing the whole world at every single moment, reconstructing the state from scratch at every opportunity, right? Obviously, when I say delta, I am meaning change, engineering jargon for change. The techniques that we are going to talk about are especially useful for a particular type of application, which is financial market data, and more generally, time series data. This is data that progresses over time, streams, flows of data of a similar nature. Okay. Please, by show of hands, who understands the encoding of video using MPEG? All right. Okay. Well, this is a challenge because if you understand MPEG, then you understand delta coding quite well already, and many more complicated stuff. I'm going to try to make something relevant for you. Okay. The general idea is that it is not practical to encode each single pixel on each frame, because we're talking of millions of pixels on a frame, and we're talking of maybe 25 frames per second, 60 frames per second, so it is impractical. So the alternative is, once you have compressed an individual frame using discrete cosine transforms or the other techniques, you can have sort of a snapshot from where you're going to be applying changes, and those are the iframes, and then you apply changes to the iframes via P frames, which are like predictive. This is just a record of the changes that happen, or B frames that's not the change with regards to the last frame, but also to the changes with regards to the next frame. All right. Again, what we're doing is avoiding describing the entirety of the state from scratch at each step. So, one design mistake that is baffling to me is that financial exchanges, for example, many in the world have adopted Martin Thompson's design for simple binary encoding, including, for example, the Chicago Mercantile Exchange starting in 2016, I think, and many others, and get progressively adapted. And well, the simple binary encoding defines the ways to describe a data type that is a snapshot of the state of the information concerning a financial instrument, for example, and very prominently describe the ways to define incremental updates, which are the changes, the deltas, okay? And well, that's good, right? They are applying, right there, they're applying delta coding. But it turns out that if you inspect the incremental updates themselves, the variation between incremental updates, especially for a particular financial instrument, for example, like the flow of orders in terms of bids, asks, trades, etc., the variation of those incremental updates is minimal compared to the size that it takes to represent the entirety of the data type of an incremental update. So it's a very big missed opportunity to apply delta compression as in a second level, so that you reduce the data to be communicated and therefore automatically reducing the latencies. Because I hope to prove to you that delta coding it requires so little processing, especially in the part of decoding, that it on the whole reduces latencies, even if you put a step of processing in the pipeline for consumption of the data. In particular, if, for example, you are at a firm that consumes streams of market data, and internally you have to disseminate it across the network, the latencies of just pushing the data out of in the network are huge. So you're always going to get ahead if you compress that flow of data whatever way you want it. I mean, if you can afford it, because the latencies are not as important. Okay, well, yes, but of course, if I am talking of disseminating data within the network, then the latencies are out the window already. So, now, the key question that we have to ask ourselves is, how are we going to quantify either similarity or dissimilarity? Because now we need to enter the territory of quantifying things so that we can apply rigorous and useful engineering techniques to it, okay? And this is what requires us to introduce information theory. So the question that we're going to aim toward right now is to define objectively, rigorously, and quantitatively something like information. So imagine that we have a lottery, that the numbers of the lottery are composed of 6 decimal digits, okay? So when the day of the lottery happens and a number gets selected on the lottery, we have one number. So my question to you is, how many binary bits, are needed to encode the information of the winner of that lottery that just happened, okay? It's a very easy question, but it introduces the logarithm, which is what I am aiming toward, okay? So you can make the approximation that 2 to the 20th power is about 1 million. It's more than 1 million, actually, because 10 to the 10 is 1,024. You know, remember the dispute between what is the meaning of a megabyte when you buy a hard drive or a terabyte, for that matter, whether it is calculated on thousands or 2 to the 10. So they are skimming a little from you if they do it on 10 to the 3 as opposed to 2 to the 10. But anyway, we just need an approximation. We can say that to communicate the winner of a lottery, we need, if there are 1 million possible numbers in the lottery, we need 20 bits to communicate that information, okay? I hope that nobody objects to this approximation, right? Now, I want you to observe that this is an exponential, because if we add 1 bit to the amount of bits available to represent information, we can double the range, right? So if you look at it from the other way around, every time that we're going to be asking what is the amount of information in something, we are going to be using the opposite operation to exponentiation, which is the logarithm. Now, if I tell you we are in the United Kingdom, I hope that my text is comprehensible. If I say Argentina won last night's football match, am I telling you something surprising? Given the context, No, right? I'm not saying much if I say something like that, right? No, I see some skepticism, okay. Because they have been winning so often, it is not news to report that they have won, right? However, if they would have lost, that would have made for interesting news to comment about. People would be motivated because there will be some element of surprise about that factual record, that bit of information that Argentina might have lost a football match. Okay, is there a way to quantify that one message conveys more information than another? I just presented to you two choices, that Argentina won the match versus lost the match, and one conveys much more information than the other. We agree on that intuition, right? So how do we quantify this? Because we had a very easy example right before, which is the numbers, the winner number for a lottery, because we know or expect that all of the numbers in the lottery have exactly the same chance. So they have like a symmetry to them, and we can treat them homogeneously. And so it's just to calculate the number of bits that we need to represent that range. But this is not as clear, right? Because these are two examples, two messages that are very dissimilar in terms of the informational content that they have. Well, the intuitive meaning of probabilities is to represent the quantity of an event of interest versus the total number of events that happened, okay? So it's like the count of the filter from the universe of events that happened. So it has got to be related to the probability. Furthermore, as I explained before, the logarithm had to be involved because that's what converts ranges into numbers of bits. Well, sorry, I went back. So when you calculate the logarithm of a probability, the logarithm of the probability of a message in a message channel, or a communications channel, the logarithm of the probability of the messages of a particular message is the intrinsic or self-information value of that message, okay? Have you ever seen this terminology introduced to you before? Okay, there's some few, but less than the last question. Okay, we're getting well. So, intuitively, if we have a collection of messages in a communications channel, the total information that the channel is able to convey is going to be the weighted sum of the information content of each of the messages. And the weights have got to be the probability of the messages themselves. Because if a message occurs very, very often, has a very high probability, then its weight on the contribution to the total amount of information in the channel has got to be high. So it's directly related. It is directly related to the probability of the message, and also directly related to the logarithm of the probability, which is the information that they convey themselves. But of course, we had to make the proviso that the logarithms of probabilities are negative numbers because the probabilities, by definition, have got to be less than 1. And we just changed the sign, and that is what we're looking for. So this is the monumental achievement of our civilization of Shannon's entropy. The summation over the set of possible messages of the product of each probability of that message by the logarithm of the probability of the message with the sign reversed, okay? So I ask again, have you ever understood Shannon's entropy before this presentation? Please raise the hands. Okay, there are many, still there are many that have done it. So the definition of closed channels of entropy really is the same as the definition by Boltzmann of entropy based on his devising of the theoretic, the theory of kinetic gases. All right? And what I want to convey to you is something truly important for the rest of the presentation, which is the model for the behavior of gases invite us to think about the amount of disorder in the state of a system that has a gas. So the link between the reality of physics and Shannon's entropy is precisely that the more complicated it is to describe the chaos in a system of gases, the more thermodynamical entropy it has. And at the same time, the more bits it is required to be represented and described. One thing that continues to blow my mind is that this is exactly the same thing as the original concept of entropy that was invented by Rudolf Clausius in classical thermodynamics. Actually, it is the experimental verification of the entropy has in the kinetic gas theory. And it is the physical reality of Shannon's entropy, all three at the same time. It's wild. So why am I torturing you with mathematics tonight? If we didn't have it, now we have a way to analyze a code, okay? So we will see immediately that delta coding involves us to use variable length codes. And if you're going to be using variable length codes, we need to encode not just the data that we wanted to represent originally, but also the data and the length of the encoding that we're using. So we are making like the problem of encoding harder because we are encoding more things. And it is just a quantitative question whether it pays off. Now, there is another reason that is truly important for all of us as software engineers, especially those of us that work in performance-related concerns day in, day out, because entropy is also the degree of surprise that several truly important components of the execution machines, the processors, have. In particular, the branch predictors, the memory prefetcher, the memory caches. So if you surprise them, because your program requires of them things that they were not expecting, then they're going to perform 100 times, 200 times more poorly than if they are able to correctly anticipate what the program or the stream of execution is going to ask of them, okay? Have you thought about this? Because it's really important. It's a difference that there are two orders of magnitude of performance in there, okay? So we need to have instruments to quantitatively reason about if we are in a situation in which we had to pick the lesser of two evils, for example, because we had to surprise the branch predictor or the caches or whatever, then how are we going to surprise them in a way that is less harmful? See, the information content has a direct relation on a day-to-day basis to the performance of applications and libraries. So, in the last part of the slide, I posit that if a benchmark doesn't emulate comprehensively the entropy of what they are benchmarking, the benchmark is no good. And this is something that I have not seen anybody commenting on it, okay? That's why I say that most benchmarking is wrong. Furthermore, emulating the entropy of real use is very hard. And we had the incentive of doing our benchmarking and test cases and our fixtures and our mechanisms, all these, to make them really, really neat and tidy and predictable even. So that is exactly anti-representative of real use. So if you didn't take entropy into account, I'm sorry, but your benchmark is very probably worth less than worthless, because you might most probably hit something misleading and counterproductive. One frustration that I have is that when I bring the subject of benchmarks in my own presentations at work or at conferences, invariably people complain that my benchmarks are weird and too apparently complicated for no good reason, okay? And it is because of that, because I am making a very conscious effort of representing the entropy and studying the relation between the entropy of my benchmark to the benchmark itself. So there are also other things. Other things that are wrong about benchmarking, which is that most people don't take into account resource contention, as if things like the memory would be infinite or the. So I can quote an example that I studied in depth. There is this library to do calculations on the game of Texas Hold'em poker that the name is Poker Stove. And every time that I would benchmark Poker Stove or see the benchmarks published by other users of this library and the author of the library, it would benchmark fantastic, really, really great, okay? So it was considered to be like something unbeatable in terms of performance. But I began to notice things that were not right. One of them is that for all of the operations involved in calculating equities in poker, it was using pre-computed lookups, so that instead of having to make a computation, it would find the result by indexing using the input. The input would be an index into a table, and the table will tell you the result, okay? And that seems to be really good, because if you are doing one lookup, if your execution environment is doing one lookup at a time against a lookup table, very, very certainly, almost assuredly, your memory is going to be able to keep up, and the access patterns are not going to be disruptive, so that you're not going to end up hitting cache misses and so on. So beautiful benchmark. But you put it to do something realistic, and then you don't have one lookup at a time, but you have 5, 6, 7 lookups at a time on memory that is random and all over the place, and then the whole performance absolutely collapses without too much effort even. So that's a contention of resources is not modeled well. And another thing that is related to this presentation, to entropy, you can see a presentation by Emery Berger that's very, very popular. It has 500,000 views on YouTube and everything. The name of the presentation is Performance Matters at the Strange Loop Conference. I picked this quote from him. Current approaches to evaluating and optimizing performance don't work. He's just saying it without qualification even. And he also says things like, for example, that O2 and O3 optimization levels are indistinguishable from each other. It's just noise, the difference. So this is how it looks on YouTube. Performance Matters, The Strange Loop by Emery Berger. But, or not. Perhaps performance doesn't matter. The law that I am sort of stumbling upon is that it is the illusion of performance what matters. But I'm not into that, so I am frustrated. Let's say that we have an example of a communications channel that has can support two messages, okay? Something along the lines of what I was describing yesterday, or a moment ago, of Argentina either won the match or didn't win, draw or lost the match. Just two pieces, two different messages. And the probability of M0 is 7/8, and the probability of M1 is 1/8, okay? So if we run the numbers, we're gonna see that we need slightly over half of a bit to represent the information that one message happened in the channel, statistically speaking, okay? That is what Shannon's entropy tells us. We need a little over half a bit. In particular, less than a bit. So we can make a very simple coding of saying that we're going to use one binary digit, one bit. 0 would mean that M0 happened, and 1 means that M1 happened. But then we will be using one bit to encode that, right? And we know that we can do better than that. How better? Well, we know that there is a limit, okay? Which is the true information content in the channel that, again, we know is Shannon's entropy, okay? We cannot do better than that. But how close can we get to it? The essence of compression is to get closer to the minimum amount of information the minimum amount of bits to represent the information. One strategy is to not code message by message individually, but to code groups of them. And so we will have something like this. And then we can use the Huffman coding algorithm, which is a very simple algorithm that I encourage you wholeheartedly to study because it is useful and interesting. And what I'm going to do is to attempt to get ChatGPT to do that for me. ChatGPT 4. Are you able to read? Do I make the fonts larger? Okay, in the warm-up, we can see that ChatGPT at least understands what Huffman coding is and the whole thing about communication channels and so on. But that's not what we want because he gave the correct answer that is not useful. Have you ever done things like this in ChatGPT? Raise hands, please. Okay. Sorry if I am showing you things that are very basic, but a lot of people have not seen this. Okay, so I believe that this is not correct because I am seeing, okay. Probabilities and the code word length. Unfortunately, this table is incorrect. I'm just going to give it a couple more tries because the randomization in ChatGPT sometimes makes it do the steps of an algorithm in an incorrect way, and that is the source of mistakes. Okay, this is a more reasonable result. At least we have the property that the cost of the same length. Well, we can continue to play with ChatGPT, but what I was trying to illustrate for you is that this is a resource that we can use to learn the whole thing. Okay, but it's not perfect, and it is like talking to someone who is very enthusiastic about what they know, but they don't really know, so you have to be very careful to accept the results. I did this while preparing for the presentation, of course, and I got a correct Huffman tree for this, and it is what I just captured for you now. So what have we doing now? Is there is an algorithm that we can learn, and it is going to give us a code that actually captures Shannon's entropy, okay? So the most important property of this code is that the most frequent messages have the shortest codes and vice versa. Furthermore, when the messages are independently distributed, okay, like the occurrence of a message has no incidence on the occurrence of other messages, then that's all there is to know about the communication channel, the probabilities of the messages. And then Huffman coding will give us the best approximation to Shannon's entropy, meaning it's going to give us the optimal, one optimal encoding for that. And here's another practical illustration of how real Shannon's entropy is, because you can actually get it with tools such as the algorithm of Huffman coding. Okay, so now that we have the necessary things to understand and talk about coding, let us talk about delta coding. Let's go over an example, which is very popular because everybody and their dog in the world uses Google protocol buffers. It is a byte-oriented format, meaning that the output of the protocol buffers with regards to integers is going to encode one byte at a time. The encoding is little endian, meaning that the least significant bits are going to appear before the most significant bits. And in the resulting code, the most significant bit, the MSB, the most significant bit is going to indicate that the code needs at least one more extra byte if it is set, or that it doesn't need any more bytes, therefore it is the end of the code if it is 0, the most significant bit. Okay, so they call it that this is, in the case of unsigned integers, that it is an encoding on base 128 because you are picking 7 bits at a time, so that is correct. And the way that they deal with signed integers, the way that you encode signed integers is not really interesting because in essence, all you need to do is to move a bit from one position to some other place in the code. Or do something like, for example, the zigzagging of making room for the signed bit has the least significant bit in the code and move on from there. Okay, so let's try to spend how much time? 1 minute in the example. I am setting in yellow the part of the input that is going to be copied directly to the output, to the code, because it is the 7 bits that are allowed to be encoded per byte in this encoding. I am setting in red the most significant bit of the byte of the code to indicate whether an extra byte is required or not. And if we start with a simple example, such as 5 can totally be encoded with 7 bits, and therefore there are no need for more bytes. Therefore, the most significant bit is 0. Another example is 65,539, which is, by the way, 65,636 plus 3. So it is a power of 2 plus 3. If I counted the numbers of zeros correctly, it is this. And you can copy those 7 to the first byte. But obviously, this segment of the input of the more significant bits cannot be encoded in the first byte. Therefore, we need an extra byte, at least one more byte. And now what we're challenged with encoding is this, but we can only pick 7 bits. So we again need another byte. And finally, we get to something that we can encode in a byte. So what is it that we end up having? This, this is the hexadecimal 83. This is the hexadecimal 80, and the hexadecimal of 4 for the third byte. Okay. So, what is it that we're doing? What is it that Google is doing? It is privileging small numbers with codes that require fewer bytes. We agree with that? Did we see that? If not, I should go back to explain it better. The longest possible code is 9 bytes compared to 8 that the representation takes normally. So that is not particularly bad. It is very simple, has that merit for sure. And if we look at it in deeper detail, it uses unary counting for the number of extra bytes, because you devote 1 bit to them, right? So you set however many bits as you need. So that's unary, the unary numeration system, right? But there is a major pitfall. which is that this scheme has high entropy with regards to the number of bytes, the count of bytes of each code. And I will tell you how to improve that momentarily. The essence of performance in our day and age is to transform dependencies of control flow into data dependencies. What this means is to do whatever you can so that you don't run into if-then-elses, but do computations and mathematics so that you calculate things unconditionally. Because they are very expensive. Not only you incur the risk of the branch predictor mispredicting, but also you tie resources in the branch predictor even if the branches are never taken or the predictor always works. So it can be that it interferes with other part of the program. For that, you use as much mathematics as possible. So one example of this is, for example, the string length function in the C library. I invite you to see the implementations out there. Most of them, you're going to see the good implementations, including glibc and so on, the one used in Linux, is to do a SWAR, a SIMD within a register, to detect the null byte, meaning doing like 8 comparisons, 16 comparisons, 32 comparisons, or byte comparisons at a time, so that you don't have that busy loop of checking for each individual character. Now, how many of you have seen the details of the design of integers for protocol buffers before? Okay, I see only 2 raised hands. But all of you, have you thought about perhaps using unary is not a good idea in this scenario, but that perhaps using binary coding for the number of extra bytes might be superior? Who thinks that binaries might be superior? Yes, several raised hands. But what are the trade-offs about using binary encoding? Are you able to quantitatively deal with them? Because if you are, then you have the power of designing codes that are going to take advantage of the actual nature of the data that you have at hand. All right? In particular, if we devote 3 bits for the encoding of the extra bytes, then we are going to have a range of 0 to 7 extra bytes. We can do something special for the rare occasion of 9 bytes in the resulting code. And we are very probably going to get ahead, okay? But there is another easier to identify mistake that is baffling. Google, the designers at Google chose an encoding scheme that increases the entropy when you are encoding. Because if they chose to use a unary encoding, that probably is a legitimate decision. But they didn't have to spread the freaking bits in the entirety of the code. They could have put the unary encoding for the number of extra bytes in the first byte where it belongs. You see what I'm saying?
The difference with this one is so synchronized. You can just get in the middle of the stream and find where the boundaries are.
Okay.
The algorithm is essentially what PKFA does by doing essentially 7 bits, but then your count bytes has essentially an extra bit for the limiting essentially the number.
Okay. Our friend in the back is telling us that this has the property that perhaps helps to recover exactly where you are in the stream. But if you look at other design considerations in the protocol buffers, this is something in which integers appear intermixed with encodings for arbitrary types of data. So being able to to recover in the middle of an integer, I don't think is very helpful, if I understood your comment. But,
No, but you can read it without schema.
huh?
You can read it without schema. Like complicated, an example is essentially like ASM1. You cannot read it without schema. It's much more efficient, but unless you have a schema, it's just local bits.
Yes. Our friend is telling us that one reason might be that you might require a schema to interpret the code versus a very simple encoding scheme that does not require a schema. I don't really know what our friend says by schema, but there might be reasons, okay? But I bring in the subject up because when you are designing codes, you ought to privilege the coding, okay? Because in principle, most times you're going to be encoding a few times and decoding far more often than the number of times that you're encoding, right? So it is natural that the encoder is going to reduce the entropy that the decoder is going to experience. So if I have a code in which I am being told the number of extra bytes that I am having to consume at the very first byte, I am getting ahead because I can do the operation to skip ahead to the next element right away. Otherwise, I would have to go over each individual byte to retrieve the most significant bit and detect when I have ended the code for the particular integer, okay? So I posit, despite of the objections that might have happened, that in practice, it is strictly inferior to spread the unary encoding over the bytes of the resulting code. And maybe I'm having a point that you guys don't like, but that is the justification for this presentation in a sense, because look, there are fallacies, there are pitfalls that our colleagues at good organizations and products that are very popular, like simple binary encoding and Google protocol buffers, they have made what I hope to have proven to be very simple mistakes to make. So then the guidance that I am trying to give you is how to identify those mistakes and therefore prevent them. But in general, I think it is on the category of unnecessarily increasing the entropy that the decoder experiences. So do the opposite, and you will have better programs, regardless. Okay. So it doesn't matter what kind of data you have in your time series streams. They can be floating point. If they are floating point, then you might choose to afford to lose precision once in a while. Identify from the format of a floating point, like for example, the mantissa might be changing very slightly from one number to a number, and therefore use integer delta coding for the mantissa. And you can use, like for example, in financial market data, prices tends to be represented as multiples of minimum increment or decrement, which is the tick. And so that's an integer number. If you do this, then you can use the techniques of variable length encoding for integers that you now have the powers to design on your own without making the mistake that Google have done, for example, hopefully. And there are also other choices, like mixing delta coding with other compression schemes, like Lempel-Sieve, Huffman, round length encoding, and so on, okay? And now I hope that you are able to, or dictionary coding, now you have the instruments to compare them and see where they are beneficial or not. There is a big problem for why I myself cannot make a general delta compression library to offer and present to you, which is we still don't have introspection. Therefore, we cannot assign the semantics of what is this compression or decompression or coding scheme that I want for the data types that I want. And the limitation is on two orthogonal dimensions. There is number one, the dimension of assigning the semantics of what is the compression scheme for a particular data type, which is necessary by itself. And also, the next thing that I'm going to talk to you about is that what do you think is going to work better? Normally, all data stream protocols define heterogeneous data in the stream, okay? Heterogeneous data means that it has data components of different types. So what do you think is going to be better? Getting the heterogeneous data stream, converting it into an homogeneous collection of streams, or a collection of homogeneous streams, like, for example, separate. They say that you have something like the order type and the prices. So that is heterogeneous because the order type and the price are of different nature. You can split that and keep a stream of homogeneous order types of all of the messages that you get and all of the prices. So you get them homogeneous. So very obviously, the conversion of heterogeneous streams to collections of homogeneous streams is going to be very beneficial. But alas, the language doesn't help us again, because we don't have the way to do that data orientation scattering. And this is something that I discussed in depth at my presentation, Data Orientation for the Win, cppcon 2021. And I want to share with you, in all humbleness, feedback that I got from someone over YouTube. The YouTuber told in a comment, there should be a better version of this talk. And well, it turns out that that member of the audience is stuck with me because it seems that I am the only one talking about data orientation in the conferences. And I don't know if those are the only members of the audience that are paying attention to what I'm saying. But be as it may, despite my failures, the solutions that I introduced in this presentation and the previous one are practical. They have been used in production and are ready to be used. So we're approaching the end of the presentation. Normally, relational databases implement the tables, and the database has collections of rows of heterogeneous data, and that is not as good to represent streams of data, like time series, has the equivalent of representing the tables has collections of columns of homogeneous data. So I very much encourage you to do that. And if you have homogeneous collections of data, then very, very likely you're going to be able to apply any sort of delta compression mechanism and get ahead in performance and compression at the same time. Additional materials. So how many minutes? 6 minutes? Great. I am sort of cheeky with my tag because I put that I am continuing the work of Alexander Stepanov, but this, in a way, is actually literal. I don't think that this is a presentation to make a formal biography of Alexander Stepanov. I'm just going to say that I am a fan, that I'm going to invoke Sean Parent to back me up on how important Stepanov is by reminding you that he said many times that he was so impressed with the quality of the source code that Stepanov wrote that he was asking himself, who programs like that? The Meraki in Stepanov's work is really clear, okay? If you don't know what the meaning of Meraki is, do yourself a favor and find it out. So I thought that it might be interesting for the audience to have a glimpse into the day job of Alexander Stepanov in the later years. Turns out that I began to work in Delta coding while the team leader for the data group at Credible Capital Management, the coworkers that I joined had already implemented a tool set that relied on delta compression for dissemination, internal dissemination of market data for the purposes of research and so on. And I had to research at one point how to improve these things and check what other people were doing. And I stumbled upon the work by Stepanov, and I took a very quick interest into that. I found an article from him, 2014, called SIMD-based decoding of posting lists. And this is, so the posting list is like in a physical book. At the end, some books have an index that for a keyword tell you the pages where the keyword appears. You know what I'm talking about, right? Because physical books have almost disappeared completely from technical disciplines. So that is the posting list of the book. And the key observation is that the posting list or the page numbers is very natural to have the encoder of the generator of the posting list to do everybody the favor of sorting the number of the page numbers. So the posting list is a monotonically increasing sequence of integers, and therefore it is amenable for delta compression because the range of the page number had to be much larger than the range of jumps of page numbers on the places where the keyword happens. So if you translate this to an environment in which you have keywords again, but you have the document IDs of plentiful places where the documents happen, then you have an interesting, useful production problem for an organization like Google, Amazon, or many others, or hedge funds that do market data too, okay? So I read in earnest that paper. It is published at Alexander Stepanov's page itself, so it's very easy to retrieve. And it goes over and it gives you a great taxonomy of all of the mechanisms known to him and his collaborators of delta coding, and the different implications that they have for different reasons. So I thought that this paper is so good that I didn't have to spend too much time into describing delta coding for you, the actual details of delta coding, because you can go to this fountain and drink from it, and it's probably going to be better because you can do it offline and at your own leisure. I just needed to introduce the principles, and I hope they were useful. However, I want to comment on something, which is this. By just looking at this paper, immediately you get the rigor, the quality, the great results that are typical in the work of Stepanov. But I saw that he ran into a dead end, that the work that he did ran into a dead end. And the dead end is the use of the assembler instruction of shuffle bytes, P shuff B. And shuffle bytes is like a magical instruction because it allows you to do simultaneously, in this particular example, 16 lookups into lookup tables, all right? The problem that this thing has is that if you use this instruction, that is a dead end, in my opinion, because physics do not allow for a more performant implementation of this operation. I cannot imagine that the processor makers are going to make a crossbar that needs to grow exponentially larger in the number of lookups that it can do so that it can scale upward, okay? So you're always going to be tied to Intel's SSE3 from that point of view. And yeah, Intel has sort of generalized shuffle bytes, but not quite, which sort of proves the point that I was making. There are ways that are entirely different in which you very radically avoid the need to do lookups in parallel by using SWAR techniques and so on that I implemented and got over the performance of this implementation because the SIMD that I'm talking about could scale to 256, 512 bit SIMD registers, and not only one register or one shuffle byte operation per clock, but however many bitwise operations the processor could support. So why am I saying this? Because, again, I hope to have proven to you that the mistake that Google made was an easy mistake, something easy to identify, easy to prevent. And what I'm doing is to encourage you to apply some Meraki to your designs so that you get to enjoy the satisfaction of doing something that you know is as good as anybody has ever done. That should be the end of my presentation. Thank you very much, guys. And ladies and gentlemen.